Okay, so this week for lab, we're going to be using a simulation similar to the one we used for the asteroid collision lab, where you just enter some numbers into a computer program and it calculates the physics behind the scenes and just kind of spits out the results at you. And the process we're going to be looking at today is stellar evolution and how it looks on the HR diagram, the Hertzsprung-Russell diagram, when a star changes from a main sequence star to a giant to a supergiant to a white dwarf and so on. And this simulation lets you test different starting parameters, different starting properties of the star, and see how it evolves. So the URL is in the lab handout. When you enter that URL, you'll be sent to this landing page. There are a few different levels of the simulation. We're going to be using the advanced simulation because it gives us a few more options. So if we click on that, it takes us to this interface where we just have a bunch of properties of stars and then a text box to enter in our selection for that property. The lab handout explains each of these properties. I'll go over them really, really briefly. The most important one is, excuse me, the starting mass of the star. If we wanted to simulate the sun, we would enter a star with 1 solar mass worth of mass. If we wanted a star 10 times as massive as the sun, we would enter 10. If we wanted to enter 100 times more massive than the sun, it has a maximum of 120. But let's just simulate the sun, so we'll start with 1. The metallicity has to do with how much of the star's composition is made up of heavy elements. We're not going to look at the effect of metallicity on stellar evolution, so you can just leave the second one blank. The third box lets us simulate a bunch of stars evolving at once, like if we wanted to evolve a whole star cluster. I don't think I asked you to do that in this lab, so we're just going to leave this blank and we'll just simulate the one star. The beginning time, you can start the simulation like halfway through the star's life if you want. We're not going to do that. We're just going to leave this blank and start it when the star is born. The ending time lets you set an endpoint for the simulation so it doesn't keep simulating for billions of years after the star dies. Notice that the times in this simulation are entered in millions of years, right? So stars live for billions of years. So a billion is 1,000 million. So if we wanted the simulation to run for 15 billion years, we would enter 15,000 million years, which is 15 billion. So basically, think in terms of billions and then add 3 zeros is the way to think about it. 15 billion years is 15,000 million years. Number of frames just controls the resolution of the movie it makes. I always put it on the maximum. Type of star formation, this is only useful if you're simulating a whole cluster of stars. We're not going to be doing that, so we can leave that blank. And this is really, really important. This last checkbox we want to tick on. We want to see the track that the star leaves on the HR diagram so we can trace its path. Then we click submit. And it takes a few seconds. And then it, just like the asteroid program, it tells you your parameters back at you. And then it gives you a result. And it gives you all this information about the star's life. How much time did it spend on the main sequence? How much time until it left the main? So, sorry, this first one is, when did it enter the main sequence? And the answer is at time equals 0. It just started as a main sequence star. The Hertzsprung gap is essentially the amount of time that it spends in the main sequence before it leaves and moves up to the giant. So this star lived for 11 billion years, 11,000 million, which is 11 billion years. It enters the giant branch at about 11.5 billion years. It has its helium flash and starts burning helium at 12.3 billion years, and so on and so forth. The last line of the results tells you what kind of star this star will wind up as. So this star winds up as a carbon-oxygen white dwarf. Um, WD stands for white dwarf. And there's a tutorial on the landing page if you need help with any of these abbreviations and such. So it reaches its white dwarf phase at 12.46 billion years. And also, the last thing in each of these lines is you notice that the mass of the star actually changes during its lifetime. As when a star enters the giant phase, it actually loses some outer layers of its atmosphere over time. Remember, we said that in the red giant phase, the star starts to evaporate into a planetary nebula. Those outer regions are shed. So you can see that the mass of the star actually gets lower and lower and lower as it goes on until it ends with about half as much mass as it started. So there's a table in the lab handout where you fill in basically how much time the star spends on the HR diagram, which is this number right here in billions of years. What kind of star it winds up as. In this case, a carbon-oxygen white dwarf. It also makes a movie, and I'm going to click on the movie. Oh, no, that's the data file. Sorry, that's not what we want. I'm going to click on the, down here, it says view movie here. On my computer, I think for some of you, when you click on this, it'll just open the movie in the browser. For me, it opens a download window. And so I have to open it separately. I have to download it. It's only about 6 megabytes. I have to open it separately, and I guess I'm going to have to, let's see, let's go to Zoom, stop sharing, and then start sharing of this movie. Okay, so here's a movie of this star's lifetime. The little cartoon of the star rotating doesn't really tell you much. What you want to watch is the little dot on the HR diagram. And this is a pretty boring movie because the star spends a really, really long time on the HR diagram. Notice it's moving a little bit. It's getting hotter and brighter as the star ages. And at some point, the star will leave the main sequence. It will ascend to what's called the asymptotic giant branch, the branch that leads up to the main giants, the red giants. There it goes. So it is now off the main sequence. It is now heading up to the red giant phase. It hangs out as a red giant. Oh, maybe I didn't leave it. Oh, my movie ran out too soon. So maybe I need to make this, make the number of frames even longer in the movie. Or change the end time. Let me do that. So let me look at my, go back to that browser. I feel like it should have gone all the way. 12.463, it reached its giant branch. Let me go back. Oh no, I gotta enter everything again. Let's start with a star that's a little more massive than the sun, maybe 1.5 times massive than the sun. Leave everything else alone, start at 0. Let's go to, let's see, it says it's recommended that the value be between 20 and 150 million years for high mass stars, between 150 and 15,000 million years. So let's put 20 billion. So 20,000 million. 1,500 frames. Evolution tracks on, submit. So I've entered a star that's a little more massive than the sun, which means it should live its life faster, right? This star already leaves the HR diagram after 2.7 billion years, becomes a giant by 2.8 billion years, becomes a white dwarf by about 3 billion years. So we see that it doesn't take much increase in mass to make a star live its life a lot faster than the sun. So let me click on the movie, save it to my downloads, open it up, and see if we can get the whole star's lifetime in there. So I'm going to go to Zoom, I've got to stop my screen share. I'm going to share my movie. Okay, so hopefully you can see this movie now. Move this out of the way. Okay, so there's my star. It's in the main sequence. It leaves the main sequence. It's on this asymptotic giant. There it goes. So up to a red giant, then very quickly down to a white dwarf, and then it cools and cools and cools and cools and kind of falls off the bottom of the HR diagram. So you have to make sure you make the simulation long enough that you get to the end of the star's life. So watch it again. Off the main sequence to the asymptotic giant branch, giant, bang, down to a white dwarf very, very, very quickly. So you can see one of the things that this gives you a sense of is how quick the giant phase of a star's life is compared to its main sequence lifetime. Let me really quickly switch to, do I still have the lab open? I may not still have the lab open. Let me open up the lab really quickly. Just look at the table you have to fill in, and we can talk about what you need to do for the lab. So share this. So here's the lab handout. I describe all the settings and what they mean, which ones we need to mess with, which ones we don't need to mess with. Give a quick explanation of what the output means, what the Hertzsprung gap time means, and so on. Tell you to watch the movie. And this is the chart that I wish you to fill out. Choose starting masses of the star that are 1, 2, 3, 5, 10, 20, and 50 solar masses, and run the simulation for each one. And for each one, write down how much time it spends on the main sequence, the time for that Hertzsprung gap. The final state of the star, what kind of star it is in that last line. Is it a carbon oxygen white dwarf? Is it a neutron star? Is it whatever, a black hole maybe? And find the final mass of or write down the final mass of the star in solar masses. Excuse me. Also, for each star, I want you to view the movie and to draw a sketch of the path it travels on the HR diagram. I've given you a blank one in the lab handout that you can print out and use. Or you can just draw one of these yourself on a separate piece of paper. So draw where the star starts and the path that it follows on the HR diagram, and then label that 1, 2, 3, 5, 10, 12, with the mass of the star that it was. So you'll have how many? 1, 2, 3, 4, 5, 6, 7. You'll have 7 different lines on this HR diagram showing the path, the lifetimes of each of the 7 stars that you chose. Activity 2 asks you to find the cutoff points for neutron stars and black holes by trial and error. When you enter these solar masses, you'll probably find that some of these stars wind up as neutron stars. Maybe the heaviest one even winds up as a black hole. What I'm asking you to do in that last part is just by trial and error, try different starting masses until you can zero in as close as you can to right where the transition point is between the lightest star that can wind its life up as a neutron star, and then the lightest star that will end up as a black hole. So keep increasing the mass slowly until you get a neutron star, and then keep increasing the mass, the starting mass, again, slowly until you get a black hole. Okay, so that's all there is to it. You're simulating 7 stars, writing down their final properties, plotting their paths, their lifetimes on the HR diagram, and then finding these cutoff points for neutron stars and black holes. And that is it. So I will post this video. I'll post this lab up to Canvas, and you'll have a week to work on it.